So I'm kind of in the Electrical and Computer Engineering department at NYU Tandon School of Engineering. You may know it with its older names, Polytechnic University, Brooklyn Poly. Now we're part of NYU. And I'm also part of NYU Wireless Research Center, where we carry out research in 5G. And I'm going to talk a little bit about some of the projects here. Now, it's kind of especially a pleasure to be here, talking in Shannon's alma mater as part of this very nice lecture series. And this was a picture I pulled up of your website. So I'm gonna talk about and try to argue how Shannon theoretic thinking and results that we have obtained in Shannon theory and in information theory at large have impacted and will continue to impact how 5G systems are designed. And I would like to do this within the context of cooperative communications, and I'll kind of briefly describe what I mean by cooperative communications and tell you some of the important advances we have done in information theory and communication theory and how they could potentially impact 5G systems. But before I go there, I start talk about cooperative systems. Let's kind of step back a little and kind of try to get a handle on what 5G is and what people are envisioning 5G to be. Even we get to the technical space of things, let's look at how the popular media views 5G. Now, interestingly, there's been a lot of hype in the popular media about 5G. Now, New York Times, I kind of find this picture a bit unfortunate because it's still thinking about wireless as, businessmen talking on their phones, even though, wireless is much more these days. But the text of, if you look at New York Times, captures this. So 5G, means you can download movies much faster. Now you'll have millions of devices networked. Autonomous driving. Now, Europe is also, of course, talking about 5G as well. And, The Guardian is envisioning 5G as waves of innovation that are going to disrupt every industry. Now, one piece of good news with regards to moving forward with 5G has happened over the summer when FCC voted to have 11 gigahertz of high-frequency spectrum available for experimentation. And this is a process leading to technical standards. And and FCC felt U.S. was lagging behind in Europe. So this is a big and exciting development on within the domain of 5G. But we can talk about 5G, about faster speeds, lots of terminals being connected, autonomous vehicles. But technically, for engineers, specifically for electrical engineers, what exactly is 5G? What are we envisioning for 5G? Again, the standards in 5G aren't set in stone. People are toying with various ideas. Companies are working towards 5G, but there are a few important properties of 5G or requirements of 5G that many people agree on. So, the first set of advances are going to come in terms of the data rate. So they're envisioning, 1,000-fold improvement in data rates. And where does this come from? First and maybe foremost, having more spectrum. So this can come because of combining licensed and unlicensed spectrum, or because of moving into higher frequencies and having an abundance of frequency available, as in the case of millimeter wave. Now, similarly, higher data rates can be envisioned by higher infrastructure density, smaller cells, putting more antennas per base station, as in the case of massive MIMO, and having systems with higher spectral efficiency, as in the case of full-duplex. Now, 5G is but not only about higher data rates, it's also about lower delay. So what's being envisioned is a 10-fold improvement in delay. This could come by an integrated design of the protocol stack and the core network, and moving intelligence closer to the users, as in the case of Foreground, where at the edge of the network, by utilizing the storage, we can move the content closer to the users. Now, these are mostly envisioned within the context of cellular systems, but 5G, as it is envisioned, is not just about cellular communications, not just base stations to mobiles and mobiles to base stations. A number of heterogeneous devices and applications are envisioned. Of course, the mobile broadband, machine type of communications where people talk about Internet of Things, everything being connected to Internet, and autonomous vehicles that require ultra-reliable communications. So these are kind of some of the properties that are envisioned for 5G systems. And industry and researchers are kind of working towards making advances in each of the fronts. This is all nice, but you can be wondering, where is information theory in all of this? And I would like to convince you that it is everywhere. It has already impacted in a lot of aspects of how 5G systems are designed, and there's potentially a lot more impact in the future. So just to give a few examples, when we talk about having more spectrum, the information theoretic study of wideband channels, how to utilize wideband channels, are essential in our understanding of how to use this wide spectrum in its most efficient manner. True, that spectrum is going to be a lot more that we can utilize, but we still would like to make efficient use of it for future systems. Now, obviously, information theory has done a lot of work in multi-input, multi-output systems, multiple antennas, and more recently in massive MIMO. And that's at the heart of envisioning more antennas at the base stations and how to best utilize massive MIMO. Similarly, multi-user information theoretic principles allow us to understand many aspects of 5G systems. For example, when we increase the infrastructure density, as in the case of small cells, there's a lot more interference. How do we deal with interference? Information theory has the background and tools for us to understand it. When we envision full duplex terminals, which I'm going to talk a lot more about towards the end of my talk, and deal with the additional sources of interference, again, multi-user information theoretic approach is useful. When we move intelligence to the edge of the network, now we're envisioning the same content being replicated at the edge. How do we deal with that content? What are the most efficient ways of delivering and getting that content? And last but not least, when we talk about Internet of Things, now we're envisioning different communication structures where the devices may be communicating with one another. And multi-user information theory has looked at multi-hop communications and device-to-device communication networks, which are very useful. And again, when we look into intelligence and storage at the edge of the network, or sensors communicating information, source coding and source channel coding ideas are very important. So some of these information theoretic ideas have already impacted research and development in these areas, and I believe they're going to continue to impact in the future. So what are some of the opportunities for information theory in 5G? Of course, motivated by the new settings, new communication scenarios, we can always develop new results. But also, some of the advanced technologies, such as increased computational power, cheaper storage, higher degrees of freedom, suggest that some of the ideas that we have been toying with for a number of years can now be practical and can now be adapted into 5G systems. So today, I want to make this case in the context of cooperative networks, which kind of take into account terminals being able to cooperate with one another in communication. And I want to give you an overview of the information theoretic advances, as well as how some of these ideas in their simplest versions can find their ways into 5G systems. So what I'll do is I'll start from the theoretical foundations of cooperation, which happened in the 70s and the 80s. So I call this, generation X and Y, the oldies but goldies. And then the field, even kind of not only the theoretical foundations of cooperation, but mostly multi-user information theory was dormant for a while until the late 90s. Where wireless came along, widespread use of wireless, and there were a number of very important extensions to the theory. It's like Generation Z, driven by wireless applications, and then I'll continue by giving some examples of applications, potential applications in 5G. So I'll start from the oldies but goldies of cooperative networking. Now. So, Shannon's information theory started from point-to-point communication systems. And Shannon also looked at two-way communications. Then, other simple network scenarios were investigated. The theoretical foundations of cooperation started with the work of Edward van der Meulen in 1971, where we looked at three-terminal communication channels. So the basic idea was that a terminal T1 wants to communicate with a terminal T3, and there's a third terminal T2, which is helping this communication take place. So van der Meulen provided some examples and bounds, suggesting that, indeed, enlisting the help of T2 could be very beneficial. But the biggest breakthrough came along about 8 years later in this landmark paper of Tom Cover and Abbas Al-Gamal, where they kind of described this as the relay channel. Again, a source and a destination would like to communicate, and there's a third terminal relay that is facilitating this communication, okay? So in this landmark paper, they provided a number of key results, a number of strategies for communication and capacity in some special cases. So this paper is still kind of one of the landmark papers. Now, just kind of to capture what's going on in this relay channel pictorially, again, we have a source and a destination communicating with the help of a relay. You can envision this as a combination of broadcasting from the source, right? So the source broadcasts information to relay and the destination. Again, the ultimate goal is to communicate with the destination, but the relay is around, it overhears the source to destination communication. So there's an element of broadcasting. And there's an element of multi-access when the source and the relay jointly communicate with the destination, right? Again, source is sending information to the destination. Relay has overheard source's transmission and is forwarding some information towards the destination to facilitate communication. So in its heart, the relay channel brings in two very important and fundamental communication modes of broadcasting and multi-access. So, it's, it is a very, fundamental merging of these two models. Now, some of the assumptions that were done in this landmark paper of Cover and El-Gamal and in the literature for a number of years was that, of course, the relay is causal, meaning the relay cannot look into the future, can only forward signals based on what it has heard so far. But also that the relay is full duplex. So full duplex means the relay can transmit and receive at the same time. Now, in information theory, that was a very well established assumption and very well recognized assumption. But we'll see later on when people started looking at relaying and cooperation in the context of wireless networks, they realized that this may be an impractical assumption. But now we're coming back and we're actually seeing full duplex radio. So the earlier work assumed that everything was full duplex. We'll come back and talk a little bit about duplexing assumptions. Now, to this day, so what was established in these early papers were kind of essential. And to this day, we do not know the capacity of the relay channel. So we do not know what is the best source strategy, what is the best relay strategy, and how should the destination process these signals in order to get the best rate out of this channel. So we do not know. We only know it in some special cases, but we do know some important upper bounds, on the capacity, and maybe more importantly, we do know very important and practical strategies that allow us to use the relay efficiently. And many of these strategies were introduced in the early work of Cover and El-Gamal in this landmark 1979 paper. So the first strategy is called decode and forward. In this strategy, the destination cannot decode the source signal by itself and needs the help of the relay. The relay listens to the source signal, fully decodes what the source is trying to send towards the destination, then re-encodes this, and source and the relay transmit cooperatively towards the destination to resolve whatever ambiguity is left at the destination. So again, the relay is fully decoding the source signal and then acting together with the relay to communicate with the destination. Now, decode and forward is a very good strategy when the source to relay channel is a good channel, right? So that decoding at the relay is not really a constraint. And in fact, it was shown to be optimal for this special channel called physically degraded relay channel, which essentially means that the relay has such a good channel towards the source that it can decode whatever the destination can decode. And hence, enforcing the relay to decode the source signal is not really a constraint, okay? So again, to this day, decode and forward is a very natural strategy and a very powerful strategy for the relay to use. Now, another strategy that was introduced early on is called compress and forward. So in this scenario, the relay does not try to attempt to decode. It's just observing a signal, and simply quantizes its observation and forwards it to the destination. So this, quantization and forwarding, or compression and forwarding, can be done in a smart way, realizing that the destination also has some correlated observation. So this goes under the name of Wyner-Ziv compression. Now, the compress and forward is a strategy that works really well when the relay to destination channel is a good one, right? Because that means that when the relay quantizes what it observes, it's going to be able to send it towards the destination with fewer additional errors. So compress and forward, the basic strategy was again introduced in this 1979 paper, and there's been many major improvements to compress and forward. They came much, much later, and they go under the name of quantized map and forward, noisy network coding, and it turns out that this compress and forward strategy works when you have what we call relay networks, so multiple nodes, helping communication. In that case, it turns out that each of them quantizing and forwarding their information is a very useful strategy. Okay, so the 1979 paper put forth a lot of important advances and helped us understand, what are some good relaying strategies. Then in the 80s, another Dutch master, Frans Willems, came along. He was a Ph.D. student of van der Meulen, and he extended communication scenarios from this basic three-terminal model of source and destination communicating and a third relay helping out. He looked at scenarios which he called cribbing and conferencing encoders and MAC with generalized feedback. Essentially, the idea was that suppose there are two sources, S1 and S2, that want to communicate with the same destination. So this could be uplink in a cellular scenario, two cell phones. Now, if these two sources have some side channel through which they can overhear one another's signal, then they can cooperatively transmit towards the destination, and it helps both of them. So that was the basic idea behind Frans Willems' work. And he established a number of fundamental results, taking us from the relay channel to these more complex models. So that was the extent of the major work that was done in the 70s and 80s. But then up until late 90s, there wasn't a lot of work, because people felt, the problems were difficult and the field had reached a certain level of maturity until wireless applications came along. So similar to Generation Z, the teenagers of today that are driven by wireless, a lot of the extensions to the theory was driven by wireless applications. I want to talk about some of those kind of extensions that proved to be very important for us to understand the value of relaying and cooperation in wireless networks. And I'm kind of going to touch upon, some of these extensions or, improvements to theory that were driven by wireless. First, I want to talk about how cooperation or relaying is useful when we have a wireless channel, when we have fading or losses in the channel. And I want to talk a little bit about constraints such as half-duplex. What if the relay cannot transmit and receive at the same time? So cooperation and fading channels, so there was some work in the kind of late 90s, early 2000s, where us and others realized that cooperation of users can be used to mitigate fading and create diversity. In a wireless channel, links may go in and out of outage, so link quality varies. And having cooperation enabled can create additional sources of diversity. And these papers, along with many others, motivated the idea of cooperation to leave the domains of information theory and move towards kind of more practical systems, and motivated wireless researchers from physical layer to networking layer investigate cooperation and benefits of cooperation in wireless systems. Now, it is actually very simple to understand why cooperation creates diversity. So again, think of this three-terminal network, very simply illustrated here. There's a source, relay, and a destination. So I have three links here, right? Now, if one of these links fails, so if you cut out one of the three links, you'll have two links left, and you'll realize that you'll still find a path from source to destination. For example, if source to relay link fails, source can directly talk to destination. If source to destination link fails, source can talk to the destination through the relay, right? So that essentially means that transmission still continues if one link fails. But if you cut off two links, depending on which links you cut off, you may not be able to communicate. So this suggests that we have diversity equal to 2. This is the same as a 2-antenna source. Okay, so that was the basic observation, behind this notion of cooperative diversity. Now, another practical constraint that was considered was the full duplex constraint. So again, this was a very common assumption in information theory literature because, we were looking for, best way for terminals to act. But then it was realized that for practical radios, the transmit and receive signals are 100 dBs apart, and it's very, very difficult to isolate the transmitted signal, from the received one. So in the same terminal, the transmitted signal loops back and, corrupts the received signal, and it was very hard to isolate them. So until very recently, people thought that half-duplexing, was a fundamental constraint, and full-duplex radios were not possible. So a lot of research went into investigating what happens when these cooperating terminals are bound by half-duplex constraints. So when they either transmit or receive, but not both. So it turns out that you could adapt, decode and forward and compress and forward to work in a half-duplex mode. And simple strategies such as amplify and forward, which kind of works very well in half-duplexing, turned out to be turned out to perform really well, and all of these strategies continue to provide increased diversity. But because of the half-duplexing constraint, whenever you want to use a relay, you can only kind of activate it, say, half of the time, which caused a loss of spectral efficiency. Right? So if you want to kind of use a relay to get to your destination, it's going to take twice as long, right? Maybe you'll get better diversity, but you may be losing spectral efficiency. So there were a number of papers looking at how do we trade off diversity versus spectral efficiency. Now, other extensions to theory came about in multi-user channels. So again, wireless systems inherently bring in multiple users together. So so how do we enable cooperation when we have not just a single source, single destination, and a single relay, but say multiple relays? Now, this was investigated under the name of diamond relay channel, how to utilize the relays R1 and R2 in the best possible manner. But this was also investigated as in the case of distributed space-time coding. If I can somehow synchronize these relays, I can use them as a multi-antenna transmitter, right? Transmitting signals that would otherwise be transmitted by a big multi-antenna terminal. So this went under the name of distributed space-time coding. When you have more than synchronization, you also have some phase information. You can kind of make these relays act in a coherent way and have their signals combine at the destination. So giving you some beamforming gains. But so that goes under the name of distributed beamforming, but that requires a lot of phase information and synchronization among the relays. Which brings in a number of important and interesting practical questions, as was kind of. So this is a survey paper that summarizes advances in that area. Now, other ways of cooperation and relaying could be that, say in an uplink scenario where two sources are communicating with a destination, what happens when you have a third terminal that's a relay that's helping both sources communicate? So the literature was extended to take into account such complex communication scenarios like this. Or you can have a broadcasting scenario, the downlink, aided by a relay. I'm showing you pictures, but there was a lot of work and a lot of theory that went into understanding behavior of, not only what the relay and the source should do, but how the rate region changes in the presence of a relay. Similarly, you can have two nodes that are talking to one another, where the relay could come in to help, or you could have two interfering source-destination pairs. Here, S1 wants to talk to D1, S2 wants to talk to D2. But they interfere with one another. This is a kind of very practical model when you consider two different cells in a cellular network, right, that aren't coordinated. How can a relay help both sources communicate with their destinations? Now, so there were a number of ideas put forward. I just want to kind of talk about a couple of them, which I find very interesting and brought something new onto the table. The first one came about when people looked at this multiple access relay channel and two-way relay channel. And kind of people realized that now the relay does not have to decode each source separately. Say, let's look at the multiple access relay channel. The relay is receiving both sources and forwarding a signal to the destination. Maybe the relay can decode the sum of the source signals or the combination of the source signals and forward this combination to the destination, which then can untangle all the signals. So the relay can actually decode functions of source messages and forward. It doesn't have to decode them individually. This led into research in areas that go under different names, analog network coding, compute and forward, and led into the investigation of structured codes that work well if the relay wants to decode functions of sources. Now, another set of ideas came about when the relay is used in the context of an interference channel. So, let's look at the scenario. The relay, so S2 causes interference at destination D1, and the relay can only hear S2 and forward to D1. Now, obviously, the relay cannot forward any useful information because it's not connected to source-destination pairs that want to communicate. But it is still useful to have the relay. Why? The relay can cancel interference through these red links, right? So there's interference from S2 to D1, which the relay can help cancel, or the relay can forward part of the interference that helps D1, understand what the interference signal is, decode interference, and then remove interference. So relaying is useful even when the relay cannot forward useful information. It can forward interference or cancel interference. So in a more general setting, the relay can do the usual signal forwarding, can do interference forwarding, or can do interference cancellation. And the last set of topics I want to kind of briefly mention that came about in late 90s, early 21st century is how cooperation works out in cellular networks and in large networks. So up to now, we've just had a few nodes, maybe one relay helping them out, maybe a few relays. How does this kind of manifest itself in large networks such as cellular networks? There we can envision the base stations, right? So typically, each base station serves its own cell, and there isn't much coordination among the base stations. But you can envision that these base stations are connected to a central processing unit through finite capacity links. So how do they cooperate in communication if they can exploit the presence of these finite capacity links towards the central processor? Now, this can be done in a variety of ways. If the base stations have baseband processing capability, then these finite capacity links towards the central processor are called backhaul. And in that case, typically base stations decode some information and forward hard, coded bits. And this, in the fourth generation LTE system, this kind of goes under the name of coordinated multipoint. Now, if instead the base stations are simple and they don't do a lot of baseband processing, the baseband processing can be done centrally at the central processor. In that case, those finite capacity links are called front haul, and they forward soft information, as in the case of compress and forward, so they quantize and forward. And this goes under the name of Cloud RAN, which is envisioned for 5G systems. Okay. And base station cooperation brought together a lot of ideas from, another branch of information theory, Wyner cellular model, from, MIMO channels, broadcast, multi-access, and looked at how inter-cell interference could be mitigated by base station cooperation, and furthermore, how inter-cell interference can be exploited when the base stations can cooperate. So this is the reference that I have here is an excellent overview paper if any one of you are interested. And then last but not least, when we think about cooperation in large networks, think about Internet of Things, lots of small sensors devices, a very large ad hoc network. Gupta and Kumar had this kind of groundbreaking work that said, rather than trying to compute capacity exactly, let's look at how capacity increases with the number of nodes. So that goes under the name of scaling laws. And their results were extended in multiple ways, including kind of the work by Özgür et al. That looks at the operating regimes. And one main observation was that multi-hopping or cooperation is essential for communication among distant nodes. When you have a large number of nodes, to reach distant nodes, you need to multi-hop. So cooperation is essential. Okay, so now that brings us to 5G. What are some of the potential applications in 5G of these, cooperative networks? So, you may call them Generation Alpha, who may think that they were downloaded. Okay, so, I want to kind of talk about cooperative networking in 5G and potential, implications by giving, two example scenarios. One is how relaying can be done in 5G and how useful it is. And the second one is cellular communications with full duplex base stations when the base stations can cooperate. Okay, but before we go into 5G, let's kind of step back a little and think about how or whether some of these ideas, these cooperation ideas, have found their ways into 4G, right? So we talked about cooperative multi-point where base stations cooperate. Now I'm looking at a simple relaying, so like a multi-hop, the very basic form of cooperation. So a source and a destination want to communicate, and they're going to enlist the help of a relay. Now, this idea has found its way into 4G standards, and mainly relaying has been used for either extending coverage, where the source cannot reach, the base station cannot reach too far, so uses a relay to multi-hop, or for serving hotspots, or for fighting against shadowing. And there are some 4G relay products out there, Sprint rolling out, or some products used for backhauling in small cells. Now, this is all nice, but when you look at relaying and 4G, it is there in the standards. There are some products, but the gains have been kind of somewhat limited. And the main reason for this is that the degrees of freedom are limited in 4G systems. Spectrum is scarce. We want to squeeze every bit out of the spectrum. The number of antennas are relatively smaller, and the relays, all these coverage extension, hotspots, shadowing, they've been used for power gain, which is very nice, but it only serves users at the edge. And given the half-duplex constraints, in order to use the relay, you have to give up, some of your spectral efficiency. So you're giving up some of your spectral efficiency to get power gain. It is useful for some users, but not for all. So the net impact on throughput, may be limited. Now, what I want to do is I want to kind of investigate this within the context of 5G, and I want to kind of show you that now 5G gives us abundant degrees of freedom in the case of, higher, larger number of antennas, more spectrum, and that, by its own very nature, makes relaying and cooperation a lot more attractive. And I want to give a case study for that. And I also want to see what happens when we have full duplex implementations. So first, let's look at these abundant degrees of freedom and its impact on relaying. Okay. But for this, I want to step back a little before I go there. So just kind of look at this very simple Shannon formula of capacity, right? So capacity is a function of bandwidth, can be expressed by the simple formula, right? That was one of the landmark achievements of Shannon. And when we have, you can take this formula and look at it when the signal to noise ratio is low, right? So when P is very low, then you can approximate the capacity as P over N naught, and your system becomes power limited. Meaning, if you're operating in a low SNR regime, every improvement in power pays off a lot in terms of capacity, right? This is the regime where you want to improve the received power. On the other hand, when you look at the high SNR regime, your capacity can be approximated as follows. And rather than increasing power, there you're bandwidth limited. So in the high SNR, if you could get some additional bandwidth, that would be very useful for you, okay? So this is what happens in a single link. We can operate in one extreme in the power limited regime, in the other extreme bandwidth limited regime. And what we're going to try to do is we're going to look at a cellular system and look at the effect of bandwidth, right? So we're saying 5G is going to bring in an abundance of bandwidth. So how does a cellular system behave as a function of bandwidth? When is a cellular network power limited? When is a cellular network bandwidth limited? What are these regimes? And in particular, what is the role of relaying? When is relaying useful in a cellular network, especially in the context of power limited and bandwidth limited regimes? And again, the goal here is to investigate scenarios where we have an abundance of bandwidth. Okay? So we're going to be using capacity scaling as a metric. Okay? So we're going to envision kind of a cellular type of traffic. Again, think of a cellular network where you have regularly placed base stations, and you have a bunch of mobiles, and every base station serves mobiles in its own cell. Okay? We'll assume that there are n nodes where n is very, very large, right? So you're serving a lot of users, and the cellular system operates over an area A, which scales with the number of users. The number of base stations scales with the number of users. Each base station has L antennas, which again scales with the number of users. So we're envisioning a system where more users, when more users are in the system, the cellular operator puts up more base stations to deal with those users, right? And puts up more antennas per base station to deal with these number of users. Furthermore, to model a scenario where the bandwidth is in abundance, we're going to envision that the bandwidth also scales with the number of users. So envision a cellular operator buying more and more spectrum as it gets more and more users. And with these millimeter wave systems, there'll be the model is that there'll be an abundance of bandwidth. So how would rate scale as a function of the number of users in such a system? So one can do a very simple analysis where so let's first get an upper bound on how well we can do. And let's assume that, let's look at a downlink system, and let's assume that all these different base stations can fully cooperate. So there's a central processor that can coordinate actions of all the base stations together, right? So that essentially means that I have all the base stations cooperating at the transmitter side. And let's since we're finding an upper bound, let's assume that all the mobile users can cooperate as well, right? So this is a highly idealized scenario. So then that is equivalent to an, L. Remember, L was the number of base stations. N is the number of users. I have an L by N multi-input, multi-output system. And I can figure out, the degrees of freedom in that system. Very simple. Okay? Now, this is an upper bound. And let's look at, what are some of the rates that we can achieve. And we're going to look at a simple single hopping and a simple multi-hopping scenario. So in the simple single hopping, a base station communicates with the nodes in its own cell and simply sends information to the users in its own cell. Okay, so that's essentially what this is saying. In the case of multi-hopping, we're going to use mobile nodes to kind of forward information for one another. So the base station is first going to send information to mobiles that are close to itself. Then these mobiles, take the information and transmit it towards their intended destinations through multi-hopping. And again, each cell is operating independently, right? So the infrastructure single hop is what your current cellular system does. Multi-hopping allows, the base station to use multiple hops to reach towards its destination. And in all of this analysis, we're going to assume that whatever the next cell is doing acts like interference for my cell. Okay, so the out of cell communications is treated as interference, and this is what we get. But don't look at this because I'm going to walk you through this plot. So what I have in this plot is in the horizontal axis. So remember, everything is scaling with the number of users, and so in the horizontal axis, I'm going to look at how the bandwidth scales with the number of users. So my horizontal axis is the bandwidth scaling exponent. How quickly am I increasing bandwidth as the number of users increase? Right? How quickly should I buy spectrum? And in the vertical axis, I look at how rate scales. So this is kind of the rate that I can guarantee for all users, how it per user rate scales as the number of users increase. Okay? And let's look at 4G. So I'm going to think about 4G as operating on a fixed bandwidth because spectrum is scarce, right? So that means I'm not scaling the bandwidth with the number of users. That means my rate scaling goes with this exponent, which is beta plus gamma minus 1. What are those? So beta plus gamma. So beta is how base stations scale. Gamma is how the number of antennas scale. So beta plus gamma is how the infrastructure scales as the number of users increase. And typically, you don't put more infrastructure than the number of users. So this says that beta plus gamma is less than 1, and hence that exponent is negative, which means as you put more and more users in your network, your rates are going to decrease. Okay, so this is actually bad, right? So this says that for 4G, if you want to pack it with more users, your rates are going to go down. But of course, more infrastructure means slower decrease. So let's see what happens. Okay, so before I go there, but this also says that so infrastructure, single hop and multi-hop meet at that point. There's really no need for multi-hop. Single hopping is good enough. I don't need to do multi-hopping. And I think that's partly the reason why when we have relays in 4G, the gains are kind of somewhat limited. It's not a network-wide gain. Let's see what happens in 5G. So when we increase the bandwidth scaling exponent, when we put more and more bandwidth per users, we see that single hopping is still optimal for a while for a range of bandwidth scaling exponents. And, but it stops being optimal after a point, and that point is when the edge nodes become power limited. So that means after that bandwidth scaling, my edge nodes are going to need more power, not more bandwidth, and hence improving the bandwidth is not useful. However, when we look at multi-hopping, we see that multi-hopping kind of continues to improve the rate scaling for a larger range of bandwidth scaling exponents. And furthermore, multi-hopping meets that kind of cuts that upper bound for all bandwidth scaling exponents. So multi-hopping is always optimal. And and there's a regime where kind of multi-hopping or the optimal strategy is bandwidth limited, and after a certain bandwidth scaling exponent, really kind of even the closest nodes become power limited, and the system cannot exploit increasing bandwidth, and it becomes power limited. Furthermore, when I look at the multi-hop gain, how much gain multi-hopping gives over single hopping, it is proportional to 1 minus beta. Beta was kind of denoting my base station density or base station scaling. So this says that if you have fewer base stations, multi-hopping is more advantageous, of course, because you can't reach very far and you're going to need multi-hopping. The more base stations you have, the less you will rely on multi-hopping. And this is a very natural and expected consequence, but it also shows up as part of the analysis. So, this analysis I showed you was for mobiles forwarding signals for one another, multi-hopping. We can kind of have a similar protocols for infrastructure relays. There, how the bandwidth, how the rate scales depends on your base station density and your infrastructure relay density. But overall, we observed that while multi-hopping was not a very promising strategy for 4G systems, when the bandwidth is abundant, it can be promising. Now, one last thing I want to say here is that, when you look at kind of a different cut set, you see that when you enable base station cooperation, there's potential for improvement. So our multi-hopping is a simple multi-hopping from each base station to mobiles. It does not really exploit how the base stations cooperate. We do not consider there. Potentially including base station cooperation could give us more gains. Now, so how much time do I have? Am I done or?
Well, we're pretty near.
Okay.
Another 5 minutes or so.
Okay, so maybe I want to very quickly kind of talk about full-duplex, just to give you an idea of what full-duplex is. So again, information theorists loved full-duplex, and then practitioners said that it was not possible. Up until a few years ago, that was the consensus. But then a number of groups, came about building actually full-duplex transceivers, and they did this by kind of putting together a number of cancellation technologies in the analog domain, digital domain, and by kind of separating the antennas, and realizing that even though there's a residual self-interference, it can be low enough to enable full duplex operation in certain terminals. So there's been a lot of interest in the kind of in the academic world on this, but it's not just an academic endeavor. There was a kind of commercial, ideas on commercializing full duplex transceivers as well. So now, kind of what would happen if we enabled full duplex radios? And in particular, we talked about base station cooperation. How does it help when we have full duplex base stations? So the standard half duplex operation is base stations, communicate with the mobiles in, say, one time slot or in one frequency band. And in another time slot or frequency band, the mobiles communicate with the base station. So this is done in a TDD or FDD fashion. If we had full duplex cellular, where the base stations are full duplex, suppose only base stations, then we can do uplink and downlink at the same time, right? So this is great. We're going to get a factor of 2 improvement. Well, not quite, because there are now a bunch of additional sources of interference. Self-interference from the base station. Base stations can cause interference to one another. Mobiles that are transmitting uplink cause interference to mobiles that are receiving in the downlink. This could happen in the same cell. This could happen in cells next to one another. So now there are all these additional sources of interference. So the question is, is it really useful to look at full duplex when we have all these sources of interference? So what I'm going to show you is a simple analysis where we kind of looked at this. All these additional sources of interference. We used kind of a Wyner type of cellular network, tools from information theory, and we said, well, how much is full duplex useful when we have base station cooperation? Okay? And you'll see why base station cooperation is important here. Okay. So here in the horizontal axis, I'm looking at the capacity of the front haul capacity. So that's the, how much rate I can push from base stations to the central processing unit. So the higher CU is, the more I can combine the base station signals. And in the vertical axis, I have rate. Okay? And the blue kind of distance shows the gains that I have from base station cooperation when I have half duplex base stations. And the gains, the red one shows gains from base station cooperation and full duplex. So one thing that we see is that when we have full duplex, base station cooperation is a lot more useful. Why? Because when the base stations can talk to one another, they can mitigate, they can remove part of the interference the base stations cause to one another. Okay? But then a big source of interference is the uplink, downlink interference that the mobiles cause for one another, which I'm going to talk about that right now. But the gain that you get from full duplex is, we were expecting a factor of 2, right? Because we can do uplink and downlink at the same time. The net gain that we see is about 1.7. And the reason is there's still some residual interference among the mobiles. That is very hard to mitigate. And to mitigate the interference among the mobiles, you can use, successive interference cancellation. So you can kind of try to cancel, remove the interference and then get your own signal. Or you can do some intelligent scheduling so that the mobiles that cause a lot of full duplex interference to one another are kind of scheduled at different time slots. Okay? So nevertheless, this analysis shows us that cooperation is essential when you're envisioning future technologies such as full duplex. Without base station cooperation, it is very hard to mitigate some of the additional sources of interference that you see as a result of full duplexing. Okay, so in this talk, I try to give you, a case study within the context of cooperative communications on how we moved from Shannon theoretic concepts to 5G applications. And I gave you, a couple of examples of potential gains that Shannon theory can have an effect on 5G systems. So maybe so what's next, right? For information theorists and for wireless engineers, there are still a lot of many interesting open problems in information theory. We don't even have an understanding of how the relay channel works and the capacity. Some of them are difficult problems, but then there are some new problems inspired by technology. And also some of the old techniques that we've known about relaying for a while. Now it can be a lot more advantageous in the context of 5G. So those are for researchers, for future engineers, right, the students. So many of these advanced technologies have their roots in information theory. And I will argue that, information theoretic thinking allows engineers to dig deeper and innovate. So one of my kind of favorite authors is Atul Gawande, who's kind of a medical doctor. But he writes a lot about science and medical field. So in his graduation speech, Caltech graduation speech this year, he said that even more than what you think, how you think matters. And I think that's the goal of technology or education in my mind, is to kind of teach students how to think and understand the fundamentals. And I think as an information theorist, we have Shannon to thank for teaching us how to think and how to understand essences of communication systems. So with that, I'll end. Thank you.
It hasn't been easy.
Whoa!
The robot falls, it breaks.